since it's 9 o'clock, I'm going to start off by introducing our speaker, and then we can get started. So thank you all so much for coming to our AI Institute seminar series. Today we have Professor Olga Fink, who's a professor of intelligent maintenance and operation systems at EPFL. She's also a research affiliate at the Massachusetts Institute of Technology and an expert at InnoSuisse in the field of ICT. Her research focuses on hybrid algorithms combining physics-based models and deep learning algorithms, hybrid operational digital twins, transfer learning, self-supervised learning, and deep reinforcement learning. Today, she's going to be giving us a wonderful talk on momentum-conserving physics-informed graph neural networks for dynamical systems. And without further ado, I'll let you begin.
Thank you so much, Sajida, for the invitation and for the kind introduction as well. And thank you very much all for joining and the interest in our research. Before I start, I actually wanted to get a bit of your opinion and to get your perspective. And it actually has been a question that I've been asking different audiences. Let's see if it works. Okay. I've been asking the question to different audiences, and I was getting different perspectives. And given your background, I wanted to ask you really your opinion. What do you think is the biggest challenge in applying machine learning to engineered systems? So it's very easy to join online. Just scan the QR code and choose one of the options. And the options that I present is either lack of data, lack of interpretability, that violation of physical laws, is a generalization to unseen conditions or new configurations, is it the lack of extrapolation capabilities, their inability to predict for a very long prediction horizon, or is it something else that is not listed here? We have 5 people who answered so far. I understand it's morning in Seattle, but still, I hope you're a bit more active. So I give you one more minute to respond, and it should not be difficult to join with a QR code. There was a message in the chat, is it?
Yes, there's a message from Nick saying
yes, I saw, yes. Let's see. Well, again, it's something seems to be a problem with the clicker. Seem to be the majority of you, 50% believe that it's generalization capabilities, 33% it's that extrapolation, and it's violation of physical laws and lack of data. That's actually interesting. There was another with anchor point. None of you believes that it's actually lack of interpretability, and none of you is concerned that may not be able to predict very long prediction horizons. Thank you very much for your perspective. It's really quite surprising because I was seeing it from different perspectives. What people were responding, it's often generalization, but it's also often actually interpretability. Extrapolation is not mentioned that often, actually, because maybe people don't face it, face the problem. But I'm quite surprised that you're not interested in very long prediction horizons, which could be quite relevant, actually. Okay. So obviously we are quite interested in dynamics models, and that's why I thought in the interest of the AI Institute actually quite similar to what we have been working on, because particularly we're interested in engineering applications, and often what we actually need is some type of digital twin applications that we need to develop for complex engineered systems. And if we consider what is actually the objectives of the different types of of digital twins that we need to develop. On the one hand, we need them to simulate and to generate additional scenarios, for example, but often we need them to forecast under new conditions to evaluate different scenarios. And this is actually where we would require quite long prediction horizons. What we often are interested in is really in detecting anomalies, and we can actually use digital twins for those applications. And one of the applications as well is to be able to infer quantities that are actually not directly measured or not directly observed and infer them from those digital twin applications. And if we consider what are actually the attributes of an ideal dynamics model for digital twin applications, and we obviously have quite some requirements on the input data, and obviously they need to deal with noisy input data. But we also need them to learn from trajectories without specifying, for example, the material properties of those models explicitly. So we need them to be able to learn from observations and from data. So these are requirements on the input data. But we obviously also have requirements on the output data. So even though you're not interested too much in long trajectory rollouts, it's actually what we would require for quite a lot of applications, particularly if we would like to analyze different scenarios and compare them. But what we also would like our input to be is that the input that we provide to the decision makers is really interpretable and explainable in terms of the underlying physics. And because depending on the decision that we need to take, they often need to be applied in a very efficient way, so that in an online prediction manner. And if we consider the generalization capabilities, this was one of your, kind of the two of your favorites, we would like the models that we develop to be able to generalize to unseen operating conditions, but we also would like them to be applicable really in an extrapolation setup. And so not just to generalize within the in distribution, but to be able to be applied to something that we haven't even developed the models for. And if we consider what would be the traditional approaches to model dynamics, and the simplest one would be to develop some lump parameter models. They're obviously able to output everything that we're interested in. They're quite fast and quite efficient. We can apply them for long trajectory rollout. They would be still applicable with some noisy input data, but we would need to really specify the parameters explicitly. And for anything that's beyond the model that we calibrated it on, we need to recalibrate it on a new setup or a new data set. Then we could say, well, we also can go to finite element analysis. This is where we would actually be able to do quite a lot more, but they obviously have some limitations as well because they are not computationally efficient. We would still also need to redefine them for new trajectories, for example, and we would need to do the remeshing or to adapt them to new boundary conditions. And obviously, we have the data-driven approaches. They are computationally very efficient. Obviously, they are not very interpretable. They usually fail in cases of long trajectory rollout if we are applying them in an autoregressive manner, because then they would start accumulating error quite significantly. But obviously, they can learn from trajectories without specifying the material properties, for example. But they, again, would not be applicable in generalization setups, depending on how representative the data set was. But also, they are typically not very good in extrapolation as well. So coming back to those requirements, what I wanted to discuss with you today is particularly focusing on this main aspects. On the one hand, obviously learning from trajectories, but also how can we really achieve something that is better generalizable and is even able to extrapolate as well. And not surprisingly to all of you, we have been, or the community have started to integrate prior knowledge and physics into the learning models in order to achieve better performance, better generalization, and better rollout properties as well. Um, There have been generally three different types of bias that can actually be integrated into the models. On the one hand, we can act on the input itself. So this is observational bias. We could generate additional samples from simulations, for example. Then we can make them more biased towards a specific operating condition that was, for example, not observed. We can also act on the architecture itself. So this is inductive bias, that we are adjusting the architecture more to the problems that we are dealing with. And ultimately, we can also act on the learning bias and integrate physics into learning objectives. And obviously, physics-informed neural networks has been thriving quite significantly, and this is particularly in the learning bias. So this is where we introduce the physics in the objective function. But what I wanted to focus with you today is really focusing on the inductive bias. How can we actually integrate more physics into the model architecture itself and to align the model more with the type of problems that we're aiming to solve? And as some of you already mentioned, and is mentioned in the title of the talk as well, one of the very intuitive ways to integrate inductive bias is really to integrate them or to consider pairwise interactions. And if we consider engineered systems, doesn't matter actually what we consider, we can represent them already quite inherently as graphs. So obviously the mass spring systems already look quite like graphs, but we can also represent bridges and beams as graph architectures, and also sensor networks and any type of infrastructures, but also in industrial settings such as water or district heating, or even industrial processes can actually also be represented as graphs, even if we don't have the physical graph underlying. We can infer the graph by learning the similarities between the time series, for example. So if you want to model the system, the pairwise interactions with graphs, what has been thriving quite a lot is that graph neural networks actually already inherently capable of representing those spatial relationships between components and observations and signals, and learn those physical properties. And the idea would be, for example, that by just observing of how this mass spring system moves over time, that we would be able to infer the spring properties, for example. If it is a linear spring, obviously it's a rather simple task, but if it is a nonlinear, it becomes much more difficult. But if we consider a human body walking, and obviously we can also represent the human body as a graph as well. And one of the tasks would be that we're inferring forces that are actually acting on the joints without ever measuring them directly, which is obviously a difficult task to measure. So this is really behind what is behind those learning pairwise interactions. So it's not just that we are interested in the direct quantities, such as, for example, the dynamics of these masses, but really getting also access to those properties that have not been observed. So this is also why, for example, transformers would not allow us to do that directly. We would be obviously able to predict the motion of the masses, for example, but not getting access to something that has not been directly observed. And if we consider an engineering example, the idea would be here, for example, inferring changes in the wind turbine blade stiffness by observing the motion measurements and then really detecting, inferring them in an unsupervised way without having a direct input on this blade stiffness parameters and specifying them in the simulation. So as already mentioned, graph neural networks have been quite a thriving field. And one of the directions that has been applied, particularly for in the setup of physical simulations, have been graph neural simulators that have been proposed by or driven particularly by DeepMind group. And the idea here is that very simple. Let's assume we have this very simple mass spring system, and we would represent each node a mass as each mass as a node, and we would represent each spring as an edge. And once we did that, we can start infer or kind of encoding also the physical properties or the features, both of the edges and of the nodes. So we start with this physical representation of the graph, and then we can provide the mass feature, the node features, which would be the vectors of the position and the velocity, and the edge features would be the vector of the relative displacement and the magnitude of the relative displacement. So basically, we are providing the information for the node and for the edge features as well. So once we have the graph connectivity and we defined also the node and the edge features, we can actually start encoding it. And that's the typical steps that are followed. So we have first an encoding step, we have a processing step, and then we have a decoding step. And then in the encoding step, what we actually do is we just take a simple MLPs, and when we take the edge properties and then we encode them with the simple MLPs into the edge features. Once we did the encoding, we can start processing them. And in the processing step, what we actually do is we take those node embeddings from both connecting nodes, and we take the edge embeddings, and then we start concatenating them, processing them. Basically, we are doing it over several message passing steps in such a way that, for example, this node here also sees what node 3 was actually doing as well. So this propagates information in the graph. Once we pass this over several message passing steps, we can also start decoding now. And in the decoding step, what we do is we are actually predicting the quantities that we're interested in. And in this case, the quantity that we're interested in would be the accelerations. And the loss on which we train it is the computed acceleration compared to the decoder, so the ground truth compared to the decoded accelerations. And this is how we train the model to predict the accelerations. So it's quite a simple graph neural simulator that was applied, and let's take a look how it actually works. So we trained the model on 4, 5, 6, 7, 9, and 10 masses, and now we test it in its interpolation capabilities. So we apply it to 8 masses, which is obviously out of training, so it's in an interpolation setup. And as you saw, it was following actually quite closely, so it was able to generalize, but to generalize within, so in distribution. But let's take a look how this very simple setup and trained model would actually work in an extrapolation setup. And the extrapolation setup is, so we trained it on 10 masses maximum, and we apply it now to 12. And it's a very simple system. And if it would have learned the underlying physics, it should have been applicable to this one as well. So let's take a look how it works, and what you start seeing that over different kind of when the errors start accumulating, it starts behaving very unphysically actually. So it hasn't seen anything like this before. It should have been able to generalize to the setup, but it's actually extrapolation setup. So even in this very simple system, it's not able to extrapolate to these conditions. So obviously this inductive bias is not sufficient. And this is what actually motivated us to really start thinking further and to include additional inductive bias. And this is the work that I wanted to discuss with you, what we propose. So in addition to the pairwise interactions, what we include additionally as well is that we preserve the symmetry of the interactions, but we also impose conservation of linear and angular momentum. We also reinterpret how the message passing is actually computed, and we add additionally forward time integration bias. But really the main component is in fact the symmetry preservation plus the conservation of linear and angular momentum. And at the core of it, what we actually do is we start enforcing Newton's third law at the level of internal pairwise interaction. So it's as simple as that, or maybe as beautiful as that, because what we're actually doing is we're really enforcing that the interactions are following and preserving or following Newton's third law and really conserving linear and angular momentum as well. And what enables us, kind of the one of the key ingredients to enable to achieve it is that we first introduce a local reference frame that is attached to each of the pairwise interactions. And in fact, for each of the interactions, we have an anti-symmetric local reference frame. So we have the green and the red ones. And what we ensure that these local reference frames are on the one hand, SO3 equivariant and T3 invariant as well. And what it actually means is that if we translate it anywhere in space, if we also rotate it, the quantities that we compute on them really remain invariant. And this helps us to be really independent of their positions. But what it helps us to do as well is that we can actually get rid of the vector features because we can start processing only scalars. Because when we start projecting the vector features that we actually do have, because this local reference frame remain unchanged, we can then start just caring about the scalars that are actually scaling them in the different directions. So this is really also the first step that we do. So in the encode step, we start projecting the vector features. So all of the vector features that that we have, we start projecting them onto the local reference frames. And now we start only having the scalars because we have this edge local orthonormal basis, and then we just need to have this the scalar quantities that help us then to know how large the vectors actually are. And what we do then is we have the encoding functions, we have the encoding MLPs that are acting now only on the scalar features, so basically on the projected quantities of the different nodes and the different edges. So we encode the features of the receiver node, of the sender node. We encode the features of the edge as well. And this is how we process the information. So now once we encoded the features, we can start processing them. And in the processing step, as you remember, now the process is very similar to what we had in the standard graph neural simulators. We just combine the information from the sender node, from the receiver node, and also we combine the edge embeddings and the node embeddings as well from the two nodes. What we actually do here as well to help us kind of to preserve the memory, what we do is we also pass the embeddings from the previous layer to help us keep with the memory as well. So once we did the processing step, we can start decoding the properties. And as you remember, what we do in the decoding step, we predict the quantities that we are interested in. And this is now, again, a vectorization step because we currently have only been dealing with scalar quantities, but now we can decode them back. And as already mentioned, what we actually get is we get the scalar quantities, and then we just scale down with the we just scale this local reference frame with those scalar properties. And because these local reference frames are antisymmetric, what we actually get is that the forces that we get out, they are already antisymmetric, and it really, by definition and by design, we preserve the linear momentum. So the first step is actually there. So linear momentum is conserved by definition. So we now need to take care of the angular momentum as well. And the angular momentum is a bit more more complicated, because now what we do is we take the embeddings, we pass them to decoding MLPs, and then now we get the decoded angular momentum. But now we also need to take care of the contributions of the internal forces. And for that, we also need to know what is actually the point of action of the internal forces. And for that, again, we just use the weighted sum of the position vectors of the node scalar embeddings. And with that, we can compute this point of action that is shared between, or is the same between, the two connected pairwise interacting nodes. And based on this, we can now also start computing the angular momentum as well. So what we start doing, or with this information of this point of action for the internal forces, we can now start computing the torques. And again, the torques are conserved as well, which are non-symmetric in this case. And with this, the angular momentum is preserved as well by how we actually compute and process the internal information. So now we have the forces, we have the torques, and we have the angular momentum. So now we just need to compute the node updates. And for the node updates, what we do is we compute the changes in the linear velocity. We compute the changes in the angular velocity, but combining the impact of all the torques and the forces that are acting on the nodes. And with this, we're actually ready now to update the velocities as well. So for the velocity update, we just take the initial velocity that we had observed, and we can now update it with the computed change in the linear and the angular velocity. And for the position update, we just take a single step Euler integration to update this as well. And as already mentioned, what we actually do as well is we add this forward time integration bias. So we don't only, as you remember in the original graph neural simulator setup, we only had as the loss to predict the accelerations. But now what we add as well, in order to also to stabilize the error accumulation, we add an additional regularization loss, which is actually also imposing the supervision on the next time step acceleration. And because we're anyhow training on the same data, so it's not using any additional information. And this really helps us to stabilize the error accumulation significantly. And with that, I presented to you the main ingredients that we actually need. So just to summarize, what is really relevant for this framework is that we have this local reference frame that is SO3 equivariant and T3 invariant. And this already enables us by definition to conserve the linear momentum. We also have imposed this conservation of angular momentum by really considering this or conserving it as considering the two interacting nodes as an isolated dynamical system. And by imposing this at the level of two interacting nodes, we're actually imposing this at the level of all interacting systems as well. So we have still this encode, process, decode and architecture that is rather a standard architecture, but we now actually add this forward time integration bias that helps us to stabilize the error accumulation. And we also need one additional ingredient that is really not related to the architecture itself, but rather how we model the systems. So what we added in order to enable us to apply the framework at the level to any system that we are dealing with, we added the so-called virtual reflected nodes. So what we do is that for each of the nodes in the system that we consider, we add virtual nodes at the boundaries. And for those virtual nodes at the boundaries, we attach the properties of the boundaries as well. And whenever the interacting node actually comes within the interaction distance between to this boundary to the reflected node, we create an edge there. Otherwise, we just track this distance and we don't connect it. And this enables us to treat the entire system, including the boundary condition, in one go, because we only need to take care of those virtual reflected nodes for which we attach a different type of nodes. And this helps us, for example, also to represent boundary conditions that would be, for example, have a specific speed, or can really change them depending on what the boundary conditions would really be. So these are the main salient features of the entire framework. So the first three are really related to the framework, and the fourth is really rather on how we model the systems, and that helps us also to get it better, to make it more physically grounded, as well, as you will see in one of the examples. So let's start first looking into this very simple example that we had before, where the standard graph neural simulator was not able to predict this evolution of the simple mass spring system. So as you see on the left, so this is what you already saw before, and on the right now you see how this dynamical graph net is actually performing on this very simple system. And it's still an extrapolation setup for both of them. But as you see also in very long rollout setups, the model is still able to predict quite accurately. So apparently it was able to learn the interactions specifically, and also the underlying physics. Obviously, it is a very simple system, and it's not sufficient to really even present how it works. So we had a larger experiment where we had 4 different setups of 60 particles that were contained in a box with different initial velocities. Each of the spheres that were contained in the box has 6 degrees of freedom. We have rough walls with different coefficient of frictions and different coefficients of restitutions. And these spheres would be colliding with each other and would be evolving over time. And obviously, we also compared the performance not just to the graph neural simulator, but also to several other state-of-the-art graph neural network models. Some of them are actually also conserving or are supposed to conserve different properties. So on the one hand, it's the equivariant graph neural networks, it's the graph mechanic networks, and the conservative learned operator framework. It's also called the CloFNet. But before I start presenting you the results, what I wanted to show you is the evaluation of if we really learn the underlying physics, and if we are really conserving the linear and the angular momentum as we modeled, or as we integrated into the model architecture. So we took the model that we trained on the 60 particles under 4 different conditions, and we just evaluated it on this simple setup that we have 2 particles that undergo an inelastic collision. So they start with an initial velocity, then they collide, and then they repel and they evolve further. So this is the ground truth of the discrete element simulation, and this is our dynamical GraphNet model. So obviously it looks already kind of quite similar, but the question is it really physical what it learned? And this is why we looked into the quantities that were actually describing this dynamics. On the one hand, we looked into kinetic energy of this collision. As already mentioned, these are the other models that we compared to. And the black line is this ground truth, because we have an inelastic collision. So what you see that on the one hand, all of the other models are actually not able to learn this how this collision actually evolves physically. But what is interesting that, for example, the graph neural simulator, which is the simplest model of all of them, it's actually the closest to the ground truth. But interestingly, um, it does predict that no energy is actually lost, so it just goes to the same level as it was before. So again, it's kind of closer to the ground truth, but it still did not learn that how the underlying physics behind it. So obviously, this non-physical behavior of the baseline models, and this was just one of the quantities that we evaluated on this setup. We also compared the conservation of the linear and the angular momentum in all of their three directions, X, Y, and Z. And as you see, our model was really conserving it as it was supposed to do. And again, all of the other models were not perform or were not acting in a physical way. So we also applied it in an extrapolation setup where we actually applied, so we trained it on 4 configurations, and now we applied it to the same configuration, but now it was 3 times the initial velocity, which is again quite an extrapolation setup. And this is what you see now for the kinetic energy. So the black line is still the ground truth. Now it's actually orange is our model, and blue is the graph neural simulator. And again, as you see, the other models actually again not behaving physically. And our model is able to follow it actually quite closely, not the very details, but still in a very close operation. So again, the graph neural simulator is actually the closest to the ground truth, which is a bit surprising, given that it's not supposed to conserve the physical properties, but it's still working rather well in this setup. So now we wanted to evaluate it in another extrapolation setup. And the new extrapolation setup, so we still have this model that we trained on these 4 cases of 60 spheres in a rough box. And now we evaluate it on the setup that we have more than 2,000 particles, and now we have a rotating cylindrical wall. So this is on the left is the ground truth, and on the right you see our prediction. So it's maybe a bit delayed for the transmission, but basically it rotates in one direction, that it stops, then it rotates in another direction. At least visually, it already looks that it was able to follow it rather closely. But we also evaluate the average slope, because we cannot track now it becomes a chaotic system, so we cannot track the performance of each of the particles. So now we evaluate also the average slope of the XZ surface over time. And we actually unrolled it for 16,000 time steps. I know long rollouts are not of interest for you, but in fact, so it is really unrolled in an autoregressive setup. So we predict the next time step, then we use the next time step as input, and this is how we actually unroll it over time. So it's really unrolled in an autoregressive setup, and this is typically a setup where errors tend to accumulate quite significantly. But in this case, it was really able to follow it quite closely, and it was really able to handle this very new boundary conditions that it never saw before. And also it was able to be to extrapolate from 60 particles to more than 2,000. So it's quite an extrapolation setup in this case. So just to summarize some of the highlights, so it actually handles unseen boundary conditions. It extrapolates to large configurations, and it's able to predict extended time rollouts. So in this case, we did it for 16,000 time steps, which is quite a long rollout, and we are handling boundaries in a completely meshless way. So we just represent them as these reflective nodes and attach the boundary properties to them. We also evaluated it on quite some other setups. This was one of the other setups that other papers actually used to evaluate their performance. So it's constrained and body dynamics. So in this case, we have, in addition, sticks and hinges, and we trained again the model on one setup. We applied it to others, and we again compared to quite a lot of other baseline models. In this case, if we extended the set of algorithms to which we compared it to, so it was trained on three particles, two sticks at one hinges, and then we applied it to other configurations. It's 2, 4, 0, or 1 or 3. And as you see in all of the setups, our model actually performs the best. But where it really shines, and this is what you will see in other experiments as well, is when we apply it to not just one step ahead prediction, but really to multi-step rollout. So it's still trained on this just predicting the next time step, but we're applying it in this multi-step rollout. And this is the comparison compared to their best performing model compared of all the other baseline models. And the reviewers also asked us about the data efficiency and how much do we actually need for training it, because the others actually reported their data efficiency on this data sets. That's why we compared on this data set as well. So this is the number of samples and the prediction error compared to the other models. And what is interesting that our model is actually already quite or has a very good performance, but just being trained on 500 samples without having much more present observations or having this new additional samples presented to the algorithm. And even at that level, it's still performing better than the others with much more data. We compared it to some other setups as well. Again, the human body motion is quite an interesting setup. So it was actually trained on a real subject where this the pose was extracted and then was predicted. So one time step ahead prediction is 30 frames. So this would be the prediction over after 30 frames in the video. This would be in 2 time steps, and this would be in 3 time steps. But the actual task and what all the other models compared to was just predicting the 30 frames ahead, so just predicting the 1 step ahead. And this is now the comparison to the other models. As you see, again, our model was actually the best performing. GMN was again the second best. And this is actually an interesting observation. What we added in addition is at the floor, we added a reflective node. And obviously, we did not have any properties that we could attach to this. But interestingly, this model where we don't just consider the human body, but also have now also the reflective node at the floor was actually even performing better compared to the original setup. And as mentioned, where the model really shines is in the case of multi-step ahead prediction and the multi-step ahead rollout. So this was again the best performing model compared to ours, was the second best. And was working quite well on 1 step ahead prediction, but then on 2 steps it was the error was really exploding, and then in 3 time steps it was even not computable. Our model does accumulate errors still, but compared to the others, it's very different dimension. We also compared it to for protein positions. So the task was predicting the future position of heavy atoms in this case, and it was solvated in explosive water and ions. Obviously, this is a much larger input to our model. So now what we see is that our model is actually not the best performing. The best performing in this case is a hierarchical equivariant graph neural network. So it was really designed to handle this large network sizes. So our model is the second best performing here. But what is interesting, it still shines in the case of the multi-step ahead prediction. Again, in this case, the best performing model, even with this hierarchical additional added architecture, it was still not able to contain the error kind of in low regions. So coming back to the requirements that I started with, I would say the model actually fulfills the requirements that I outlined before. So we're really able to extrapolate and to apply it really in a simulation setup. So we don't need to retrain the model for any new configuration. We can train it on one configuration and then apply it to new configurations. I actually have a bit more that I wanted to share with you. So this is a real world application. It's in a bit of a so it's not quite the same network that we applied here. And also here the task was not just to predict the motion evolution, but also to predict the load. So it was a bit different architecture and a bit different setup, but a lot of the basic ideas are still the same. And again, in this case, we wanted to evaluate the performance on being able to predict on the one hand, the position evolution, but also the applied load on each of the rolling elements. And we had three different dimensions on which we varied the training data, but then also the evaluation data. So we had different levels of internal load. We had different rotational speeds, and we had different number of rollers for the rolling element in the rolling in the bearing. So the blue points, what you see is, so this was the training configurations on which we actually trained, and then the star here would be the one on which we actually evaluated. And that's what you will always see here in the left corner. So the blue is still everything that we trained on, and the star is where we evaluate. So now it is an interpolation setup. On the left, you see the ground truth, and on the right, you see the predicted evolution. And what we are really interested in is in the load evolution on a selected roller. And as you see, it's really capable of predicting it quite closely. Now we go in and out of distribution, and it would be again an extrapolation setup. So now really go outside the external load that is actually performed, the rotational speed. So now it's actually double the rotational speed. We are in the training, we only observed 750, and now we're actually doubling it. And now it still is able to perform rather well, and really to predict the external the forces on the rolling elements quite precisely and follow the ground truth. So now we go in a really kind of extreme extrapolation setup. So it's a different number of rollers. And now we're even more extreme in terms of the rotational speed. And the load that we apply now is larger compared to what we trained it on. And again, the load is still predicted quite nicely and quite precisely, and is able to follow it quite nicely, even in this very extreme extrapolation setup. And one of the additional applications that is actually is open, for which it's opening doors, is to be able to not just detect faults in the bearing, but also to track the severity of the fault. So it's kind of quite early results, but what we were able to link is the difference in between the predicted forces for the healthy conditions and the real measured forces, or the real simulated forces, and depending on the size of the or the severity and the size of the fault, it's really correlating with it quite nicely. And typically, it's quite a difficult task to be able to track the severity of the fault. So to summarize this part is it really extrapolates, it's able to extrapolate significantly. This is what I hope I was able to convince you of. we have this very extended time rollout that we apply in an autoregressive manner, and we still don't accumulate errors that significantly. And it is computationally quite efficient. If we compare it to this finite element simulations that were, for example, applied for this in the setup for the rolling element, and it was enabling us 200 times speed up compared to the conventional solvers because we were representing it really differently, and we are really able to apply it in a simulation setup because we trained it on a number of configurations, and we are able to apply it to new configuration that it hasn't seen before and was not trained on. The applications that I was sharing with you are actually quite broad and are really applicable in very different domains. And that's the very last thing that I wanted to share with you are some results that are really fresh out of the lab, because we can also extend this methodology to finite volume methods and to apply it to fluxes and to compressible and inviscid fluid flows. So basically what we do now is we actually enforce conservation of mass, momentum, and energy by aggregating the fluxes at the level of one node. I won't go into details because really it's very early results, but just to show you kind of one very interesting result. So we took it from a data set of different models and different simulations, and we actually only trained it on one data set. And these are kind of the representation of all the others. And the more red it is, the more out of distribution it would be. So for example, the green one, it would be still in distribution, and then the red one would be really out of distribution. There were quite a lot of results that have already been published on it. So these are the reported results. But just to remind you, all of these results were actually trained on the entire data set. And then it was actually an interpolation setup. For us, it was really an extrapolation setup because we only trained on one configuration and we apply it to all of the others. And it was still performing kind of very well, even on the strong out of distribution scenarios. And these are just some of the results. So this is in distribution. This is so at the bottom is the ground truth, and at the top is the prediction. And this is the mild out of distribution. Again, at the bottom is the ground truth, at the top is the prediction. And this is the strong out of distribution. And again, it's on this visualization, it already looks it's following the dynamics quite closely. So just to summarize, what I actually wanted to present to you is really different ways of integrating inductive bias. And as you saw, is that the models were really trying to align their model architecture to the problem or to the setup. I was able to show you improved performance, obviously, but what is really more important is this improved generalization, extrapolation capabilities, because it opens new door by not just training everything, training models and everything that we're interested in, but really to be able to apply it in simulation setup and transfer trained models to new configurations. And we were able to have very long prediction horizons. So this was actually part of the research focus that I was sharing with you. So this is more in the combining the physics-based and the learning methods, but we have been working on in a bit broader research focus. And before I finally end, I would like to thank my amazing team, but also past and current industry collaboration partners, and obviously also to our funding agencies that have been generously supporting our research as well. And with that, I'm happy to take questions or to have a discussion if time permits.
Thank you so much for the really nice presentation. There are some questions in the chat already, and there's a few of us here in person. So If anyone here has any questions, otherwise I'll take the ones in the chat.
So there's a question on what
Yeah.
type. I can go back actually. What type of neural networks are applied? Maybe I was not that explicit, but it's actually just normal MLPs. And it's quite simple ones, but we apply specialized MLPs for the different encoders, for the different processors and the different decoders. So it's really kind of very simple MLPs applied here. No, it's not CNNs that are applied, so it's really just normal MLPs because also like yeah, it's a rather simple mapping that's performed there, but it's really disaggregated for the different steps and the different functions. There was a question, generalization, extrapolation are close together. So at least for us, I don't know what the question was referring to. I can try to answer maybe. Um, um, Halon could ask again or adapt to it. But for us, the difference is it in distribution or out of distribution? And in many cases, we still need to generalize to new conditions. But in this case, we're not going beyond, for example, the size of the system or not beyond uh, the 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 configuration that we looked in. Maybe a good example is really this the setup of the rolling element bearings. So generalization would be in this case something that the model hasn't seen before, but it would be still kind of covered by the range of the data that was used for training. And extrapolation would be something that is really going beyond the parameter range that was used during training.
There's a
Sorry, I
question.
did not quite understand. So the measurements, kind of the measurements are really the acceleration. So I don't know if you're referring, but it's actually just going back. Probably you're referring to this. So what we actually, so this is our loss function. So these are our observations. So we only use the accelerations as observation. And then in the loss function, this is what on the one hand we predict, but also we add this regularization step, the additional regularization loss for the next time step acceleration. I hope it answered the question. But just as a reminder, what Graph Neural Simulator is actually doing, they're using the first part of the loss. So it's only the second part of the loss that is different, but basically it's kind of the same information, but just a one type step further. So it's not any additional physical information that we're adding in the loss function. There's a question, where do you consider measurements to be made at each node or at a subset of outputs? So in this case, what it's trained on would be really on the position of the nodes. So this is kind of the measurement is really the position of the nodes. This is the information that we're using. I'm not sure because the output is again there because we are predicting the position or we are predicting the acceleration of those nodes. But it's the same as so our observations is the same as the output. There's one question for my own clarification. Did you calculate and impose the physical loss as another feature added between each two nodes, or let the network learn it? So what we really impose is how do we create those local reference frames? So this is really something that this is imposed by design. And then the way the physical laws are actually designed is by how we process the information. So we don't impose any additional information, but really it's how we process and compute and update the quantities. Because, for example, here what we do is we compute this decoded point of action, but it's a learned decoded point of action. But we use this point of action in order to update the decoded rotational torques. And this is how we then update the linear and the angular momentum. And obviously, based on this, then this is where the loss is actually computed. So if it does not learn it well, then the loss would be obviously much higher. So the way we impose the physics is how, on the one hand, how we design this local reference frame, but on the other hand is how do we process and compute these intermediate quantities. Obviously, we don't impose anything there, and the only supervision that we provide is really just on the acceleration. But in order to get it right, it really needs to get the intermediate quantities right as well, because otherwise the accelerations will be incorrect. But because we are updating this intermediate quantities in a physical way, this is why it also needs to learn the underlying physics. I hope it clarified the question. So it's we're not adding any additional losses. For example, in the case of pins, where it's really explicitly encoded in their learning objective. It's really how the system is actually designed. This is why it's really an inductive bias, because we adjust the architecture to the problem. Any further question?
I'll ask just a quick question before wrapping up. So, the results that you have are really good, especially for the long-term predictions. And you're able to get very long-term predictions, but then there seems to be some kind of limitation after a certain rollout. Is that something that you would focus on, or do you feel like just having a model that can give such long-term predictions compared to other models is good enough for the problems that you have?
So we're obviously working on improving the architectures and kind of adding more inductive bias to it. I will not disclose too much, but we already adjusted the architecture slightly. And with that, we were actually able to improve the performance again. But it was not like it did not motivate us to improve this rollout performance, but really to improve the model and extend it to new setups. But interestingly, it was really helping with the rollouts because the results are already published. I only presented the published results, but by now we have actually quite some improvements. For example, for the human body walking, where it was kind of predicting it in a better way by modifying the architecture, kind of adding additional inductive bias to it.
Thank you. There is one more question in the chat, but I know it's past the hour, so maybe this could be the last one.
Okay. What is the highest inference time in your experiments? Have you done any profiling to identify bottleneck? Which computation takes more time and resources? In the V2 version of the dynamic graph, you mentioned ablation results. Set up supplementary. Have you included other combinations on your ablation studies? Thank you for the question. Yes, indeed. So in the most recent version, we also evaluated the computational overhead that we have. Because compared to graph neural simulators, for example, we have this additional computations that we need to perform. And this is what gives kind of some additional computational overhead, also the inference time. Obviously, the training time is rather fast because we have the MLPs, but at the inference time, but also the computation time, it's a bit more computational steps that need to be performed. Just to remind you, so what we're actually kind of going back here, for example, when we start updating the quantities, so we need to compute these additional quantities. So this is what gives additional computational overhead. If we evaluated any other activation functions, so we actually did, we did not evaluate it in this setup, but we evaluated it on another paper, but it was not quite the same. Interestingly, GLU were performing the best in that setup, and we really evaluated different activation functions. Yes, so there is kind of a bit more insights on this. And for the computational perspective, yes, it's a bit more computational overhead compared to GNS. But actually, we don't consider it to be significant given that we don't need to retrain them. And this is where we would really gain, because yes, yeah, it's a bit computational, more expensive, really insignificant, but we can apply it in a simulation setup that we know we don't need to retrain them for any new configuration. And I guess this is not unbeatable in this case. So then for this one, we cannot even compare the models.
Okay, thank you so much for the amazing talk. I think that's the last of the questions, and I know it's late there, so I don't want to go over too much. But thank you everyone for joining, and thank you for the wonderful talk.
Thank you so much for the invitation. Thank you everyone for staying so long and for the interesting questions. Yeah, please feel free to reach out if you have any additional. But
Of course.
yeah, thanks a
Thank you.
lot. Also, was a pleasure discussing with you.
It was a pleasure having you. Thank you so much.
Have a good day ahead, actually.
Yes, thank you. Have a good evening, I guess.
I was actually teaching this afternoon,
Mm,
so I may have talked already too much this
yeah,
afternoon and evening. Have a good day ahead.
thank you so much.